Hi there, my name is Annie Moore, and today is Thursday, April 11th, 2024, and today we will be discussing two of the problems from the Unit 2 Case Connections assignments. So let's dive in. So the first case that I decided to look at further is case 2. So a 16-year-old female is recently diagnosed with a deficiency of muscle glycogen phosphorylase. She and her family are concerned and ask the following questions. So her first question is, I'm not sure I understand the issue. Can you explain how muscle glycogen is used normally during exercise? So our bodies store extra glucose as glycogen primarily in our liver and skeletal muscles. In our skeletal muscles, glycogen serves as a fuel reserve that could be ultimately broken down into glucose through a process known as glycogenolysis. Subsequently, the glucose produced from glycogen enters the glycolysis pathway to produce ATP as an energy source when our muscles contract. As mentioned, you have a deficiency of a muscle enzyme called glycogen phosphorylase, which is involved in the first step of glycogenolysis. Normally during exercise, muscle glycogen phosphorylase is activated by AMP, calcium released by your muscles, and epinephrine, your fight or flight hormone. However, your body lacks this enzyme, so it can't be activated, and so therefore your muscles cannot break down glycogen into glucose. Ultimately, this leads into a cascade where your muscles cannot produce enough ATP or energy to support themselves. This condition is also known as McArdle disease. So going back to your second question here, I really like to take long walks. Will I still be able to do this with my friends? Yes, you will still be able to go on long walks with your friends. Your skeletal muscles can use other substrates like free fatty acids, amino acids, ketone bodies, and glucose from your bloodstream to produce energy. Walking is considered an aerobic exercise, and during aerobic activities, your skeletal muscles produce energy primarily from free fatty acids that are released from your adipose or fat tissues. However, in general, you may feel more muscular pain, cramps, or weakness while you exercise in comparison to your friends. So don't forget to take breaks if needed, okay? And then moving on to your third question, as a result of this deficiency, will I need to get up at night to eat to maintain my blood glucose levels? The answer is no. So remember I said that glycogen is primarily stored in our liver and skeletal muscles. So glycogenolysis in the liver supports your blood glucose in the fastest state because of an enzyme called glucose 6-phosphatase. So skeletal muscles don't actually have this enzyme. So glycogen that is being broken down to glucose in your skeletal muscles does not influence your blood glucose levels at all. And then moving on to your fourth question, do I need to worry about producing excessive lactate during intense anaerobic exercise? The answer is no. So anaerobic activities such as weightlifting and sprinting are more dependent on glycogenolysis, or once again the breakdown of glycogen to glucose in your skeletal muscles. So because of your deficiency of the enzyme glycogen phosphorylase, your muscles lack glucose derived from glycogen. So that actually means that there's less glucose that can enter glycolysis. Glycolysis is a metabolic cascade of steps that converts glucose to pyruvate, and then subsequently pyruvate is reduced to lactate in anaerobic conditions. So in your case, there's actually less glucose entering glycolysis, so that means less lactate is being produced. So let's move on to the second case that I decided to look at a little bit further, and that's case 4. Previously healthy 2-month-old female presents with jittery spells several hours after breastfeeding. Her mother reports she has not given the baby anything to eat other than breast milk since birth. The baby has only recently been sleeping for more than 2 hours between feedings, and that's when the mother reports these symptoms started. Laboratory results are consistent with hypoglycemia, or low blood glucose, but are otherwise unremarkable. Epinephrine is administered and there is no increase in blood glucose, but there is an increase in blood lactate. Physical exam reveals a liver edge 4 centimeters below the right costal margin. Percussion of the right chest and abdomen confirms hepatomegaly, or an enlarged liver. Blood glucose levels increase after breastfeeding, but she cannot maintain blood glucose levels within a normal range during fasting. So based on the information above, which of the following is the most likely diagnosis of this patient? So A, hereditary fructose intolerance, B, galactosemia, C, glycogen storage disease, or D, glucose 6-phosphatase dehydrogenase deficiency. So we can actually immediately rule out A, hereditary fructose intolerance, because fructose is found in fruits. The mother mentioned that her baby has only taken breast milk since birth, so the infant has not ingested fructose. Therefore, her symptoms can't be related to hereditary fructose intolerance. Now, moving on, we can also rule out D, glucose 6-phosphatase dehydrogenase deficiency. Glucose 6-phosphatase dehydrogenase is an enzyme found in the pentose phosphate pathway, which is an alternative metabolic pathway to glycolysis. Individuals with this deficiency primarily does not have issues with maintaining their blood glucose. Instead, they typically have symptoms related to hemolytic anemia. This is because individuals with this deficiency cannot generate NADPH from glucose 6-phosphatase. NADPH is used for the reduction of oxidized glutathione, and the reduction of glutathione is essential for removing hydrogen peroxide to further prevent cell damage and cell death. And this is especially important in red blood cells because hydrogen peroxide is produced from reactive oxygen species as a result of continuous oxidation of hemoglobin. And it's also important to note that red blood cells lack a mitochondria, so this pathway is the only method to produce NADPH. So individuals with this deficiency have an accumulation of hydrogen peroxide that ultimately leads to health problems related to hemolysis, not hypoglycemia. So now the infant presents with hypoglycemia and hepatic megaly, or an enlarged liver. These symptoms could be seen in B, galactosemia, or C, glycogen storage disease. So which one is it? So let's talk about galactosemia really quickly. So in non-classical and classical galactosemia, there is a deficiency of either the enzyme galactokinase or galactosyl uracilate transferase, or GALT. Both enzymes are important for converting galactose to glucose. And lactose is present in milk, and it's ingested and broken down to galactose and glucose in the intestine. In the liver, galactose is phosphorylated to galactose 1-phosphate by galactokinase, and then activated by GALT. Individuals with galactosemia lack the enzyme galactokinase, or GALT, which leads to the accumulation of galactose in the bloodstream and in the liver, which further inhibits hepatic glycogen metabolism. Now, the key hint in this problem is that epinephrine was administered and there was no increase in blood glucose, but there was an increase in blood lactate. So epinephrine stimulates glucose production from glycogen through the process called glycogenolysis in the liver and skeletal muscles. And we kind of talked about this in case number 2 that I talked previously. Epinephrine Epinephrine also stimulates fatty acid release from adipose tissue. In the liver, glycogen is the first and immediate source of glucose for the maintenance of blood glucose levels. Therefore, an increase in epinephrine levels would signal the liver to break down glycogen to support blood glucose. For an individual that has galactosemia, the administration of epinephrine would still increase blood glucose, since there is nothing pathologically wrong with their glycogenolysis pathway. However, in this case, for this infant, the administration of epinephrine would still increase blood glucose, the administration of epinephrine does not affect blood glucose, which means she's unable to use glycogen. So the answer is most likely C, glycogen storage disease. Another key point is the infant's blood glucose levels during breastfeeding increase, but she was not able to maintain blood glucose within a normal range during fasting. So once again, the liver is responsible for maintaining blood glucose in the fasted state. It does this initially through glycogenolysis, the breakdown of glycogen into glucose. However, since the infant has some form of a glycogen storage disease, it's not able to utilize glycogen through glycogenolysis to maintain its blood glucose during fasting. So once again, our answer is C, glycogen storage disease. Thanks for listening to my presentation, and this is the end of it. Thank you.